Okay, good morning. Just here doing a sound check for this morning's 9 o'clock lecture. Can someone let me know if you can both hear my audio, but also see the title screen for the Monday of week 6 lecture? Wonderful. Thanks very much. That's good. Fantastic. Okay, so I'll be back with you for the lecture start at 9 o'clock. See you shortly. Okay, good morning. I make it 9 o'clock, so we'll kick off with the lecture. Can someone just give me one more final thumbs up that audio's coming through okay? Wonderful, thanks very much. Let's get underway. So today's lecture, important for a milestone for a couple of reasons. One of which is that we're almost halfway through the semester, not quite. Semester recess starts on this Friday. I want to discuss with you 3 topics today, 2 of which are related to assessment items, and one of which is some technical content, and we'll discuss that first. And that technical content will actually feed into the first of the assessment items that I want to discuss with you. So the 3 topics I want to discuss with you today, the technical content relates to something called interpolation, and I'll say what that is, and I'll put it in context, and I'll give you the tools that you need to use Python to perform interpolation in just a moment. But also want to talk about assessments for the course, and you'll see them listed there on the screen now. I want to talk about assignment number 1, which we're releasing today, and I definitely want to talk about the midterm quiz, which is scheduled for this Thursday. So what I want to do first is I want to cover the technical content, but and I'll do that. We'll do that at length shortly. But just to give you a heads up of where I'm coming from with the assignment and the midterm quiz. After we've covered the technical content today, and today's lecture it'll be a shorter than normal lecture, because I don't want to overload you with new technical content in the lead up to the quiz. But I do want to give you enough technical content to do the first assignment. Now, the first assignment, again, we'll discuss it in detail towards the end of today's lecture, but the first assignment is being released today. So, and it's not due until 3 weeks away. In fact, a little over 3 weeks away. No, 3 weeks exactly today. Okay, so don't feel like you're hearing about this assignment 1 and you haven't heard about it before. You're hearing about it for the first time today. So what I want to talk to you today about is what form that assignment will take, and a little bit about how you go about doing it, submitting it, and so on. And then I definitely want to give you some advanced notice of, or a notice about the midterm quiz, which, as I say, is scheduled for this Thursday's lecture slot. And I'll talk in some detail about what you can expect, how you can prepare, and in particular, how you can practice to get yourself set up and how that quiz will run. And we'll discuss that. And I'll be doing a live demo of that midterm quiz practice and hopefully answer many of your questions towards the back end of today's lecture. So we're going to start with the technical content, because the technical content, this interpolation, will actually feed into the first assignment. So the story so far, in the grand sweep of this course, from beginning to end, we've reached a really important milestone today, because just about all the language elements from Python that we need to solve interesting engineering problems, almost all of them we've already seen. So through the course of the first 5 weeks, we've seen variables with different data types: int, float, boolean, string. We've seen arrays using the NumPy library, and we've used those quite extensively. Arrays are great for storing collections of information that needs to be indexed. We've seen those and used those quite a lot. We've done quite a bit of plotting using the matplotlib library, and we've discussed the various forms of flow control. So getting computers to do what they're good at, iteration and conditional execution of code that executes only if a certain condition is satisfied. And we've also used functions. Sarah introduced to you functions last week So functions are nice little ways of encapsulating solutions to sub-problems so that you can focus on the writing of a function, debug that code, and then use that code in a larger program. And we're going to use functions again today. So actually these elements that you see in front of you, variables, data types, arrays, plotting, flow control, and functions, they are the ingredients of modern computer programming languages. And we've developed them all in some detail using the Python language. So for those of you that have been following along with the course and you're feeling like there's a seemingly endless stream of new language features that you're expected to come up to speed with and then use, that sort of stops from today. That the nature of that presentation in the course. Certainly we've got a ton of interesting content to cover, but we don't introduce new language elements from here. There's a couple of pieces that we need, and we'll look at those after the recess. But the good news is you've got the language now to solve interesting engineering problems. What we'll do from here on till the end of the semester is actually use those ingredients to solve different types of engineering problems. So the first type of problem I want to discuss with you today is something that comes under the broad umbrella in engineering applications as curve fitting. You can also think of it as model development. There are actually elements of it that overlap with machine learning, building models, building representations of the physical world that as engineers we can then derive solutions for or code solutions for. And the two common forms of curve fitting in engineering applications under that broad umbrella I've titled Interpolation and Regression. And interpolation is going to be the focus of today's lecture. The new technical content in today's lecture will almost all be on interpolation. But I do want to discuss with you regression also, because interpolation and regression are sort of to some extent overlapping. They're both forms of curve fitting. They come from a very different background, and I want to show you both of interpolation and regression. I want to show them to you literally side by side so that you can compare and contrast. Even though regression, the technical details, we're going to push back to later in the course, probably a couple of weeks after the semester break. So what you will see a couple of images of regression. Think of them as like cartoons. Think of them as like visual ways of understanding what regression is, even though I don't give you the details of how to do it, because I want you to get to see interpolation and regression together as both as elements of this sort of curve fitting process. So here's the data set that I'm going to work with a few times today. So let me point out the key points. What you see here are 11 dots, red dots on a rectangular grid. They're on a set of axes. So along the horizontal axis, we've got T, which I tend to think of as time. Doesn't have to be time, but I think of it as time, T for time. And then Y of T on the vertical axis. So for every possible value of T, there's at most one value of Y. And I say at most because you can see that the characteristic feature of that data set is that there are gaps between the dots. Now, those dots might represent the measurement from a sensor, for example. Suppose we're measuring over the course of time, we're measuring the water level or the water level in a tank, for example. So time's progressing and the tank looks like it's filling because there's some sort of trend there where the dots slowly move up over time. They don't always move strictly up. You'll see a couple of them there that look like they're about the same height. Maybe that's due to fluctuations in the amount of water that's coming into the tank. Maybe that's due to noise on the sensor. You know, you measure a certain level of water level, but the the sensor floats around at the top and it gives you an imperfect measurement of the water level. Actually, I talk about water level, but I'm just trying to give you some idea of that it's a physical, it's a process of some sort. Actually, we don't care where it comes from. They're just dots. More correctly, they're pairs of data points. So I've labeled them, I've indexed them here as TI and YI, and I'm preparing to process those data points in arrays. Now, we've seen before the use of subscripts that map nicely to array elements. Now, the values aren't of particular importance, although I do want that sequence to be repeatable. So you'll see in the code that I show you at the moment, it's called week 6 Monday or week 6 mun.py. I've actually posted that code in the lecture code channel last night, so you can run it. And I've used the random, so what I've done is I'll show you how I generated that sequence in a moment, but there's a random element to it, and I've included the seed of that random number in the random number generator in the code, so you can reproduce the exact numbers that you see here. Okay. Suppose we're engineers and we want to somehow access or predict or estimate the value of the Y function at times between the red dots. Now you'll notice the time axis starts at 0 and runs up to 100. So 0, and it does that in equal time steps. 0, 10, 20, 30, 40, and so on up to 100. So if you look carefully at the bottom of this page, you'll see the first index is the time index in this pair of numbers. 0, 10, 20, and so on up to 100. So there are 11 time steps equally spaced, 11 function measurements at those time steps. And the question is, what would we do if we wanted to know the value of Y between the red dots? So you can think of maybe we're getting a measurement from a sensor every 10 seconds. And the question is, what's the value of the measurement between the sensor time steps of 0, 10, 20, and so on? Now, that's a really common problem in engineering. To be able to estimate the value of a quantity between the time steps at which the actual measurement is made. And there are two very distinct ways of solving that problem, and they are respectively interpolation and regression. And depending on the context, one or other of them might be appropriate. So it's not like they're competitor methods, they're just different ways of solving the same problem. So let me give you a visual representation of what interpolation looks like. This is one form of interpolation known as linear interpolation. And before today's lecture finishes, you'll be able to reproduce in Python what you see on the screen there now. So with linear interpolation, we literally join the dots with straight lines. So if we wanted to estimate a quantity, the Y value at time steps between the red dots, we would simply join those red dots with a straight line and then estimate the function level at the relevant time point, because that function in blue is now quite different to the red dots. That function in blue is defined on the interval 0 to 100. So you choose a time between 0 and 100, and a linear interpolation will give you an estimate of what that Y function is. That's pretty good. And that's actually a very common way of filling in the gaps between available measurements. Linear interpolation. Just want to give you a visual representation of it at the moment because I want to contrast it with regression, which comes up on the next slide. But we will return to this example because I'll show you the code to actually, with Python, to generate that linear interpolation. In other words, in order how to generate the blue line from the red dots. This is regression. Can you see the difference? With regression, we fit a line. Sometimes you'll hear people say, oh, I fitted a straight line to the data, or I fitted a line to the data. Quite different from interpolation or linear interpolation, which joins the dots with straight lines, but the overall blue line has got these kinks in it. Regression actually fits a line to the red dots, and there's not even a constraint that the line passes through any of the dots. If you look there carefully, you'll see at time steps 30 and 40, the blue line gets pretty close to those red dots, but that's actually just chance. That's actually just chance. Regression involves choosing a line that in some sense is the best fit to the data. Very different process to interpolation. Although they sort of solve the same problem, they enable us to predict the value of a quantity between sample points. Now, regression's really, really interesting, and we'll look at it in some more detail after the recess. It's a really interesting problem, and this is just the barest tip of the iceberg. Regression gets a lot more powerful, a lot more interesting, a lot more complicated, and the applications are vast. In fact, regression lies at the heart of many so-called machine learning algorithms that you've no doubt heard about. Actually, regression is a very old technique, a very well-established technique, but it forms the basis for machine learning algorithms. So regression and interpolation, I'll just toggle backwards and forwards between them. I want to get you a visual image in your head of the different style of solving those problems. There are other forms of regression. There are other forms of interpolation. We'll see one of those today, but I just want to, you can solve, in fact, so I should have said something, it's the same data set. If you look at where the red dots are, it's literally the same data set that I'm using for both. It's just that I've solved the problem of predicting what the value of y is at the time steps between the red dots in a different way. So here we are. This is pretty much summarized what I've said. Interpolation's joining the dots. There are different ways of joining the dots, and I'll show you a second way today, but interpolation means obtaining the value of y at an intermediate point between the red dots, and regression in this case is fitting a straight line. So regression is interesting because it's almost like the principle of regression is that we have too much data. We recognize that there's some underlying process that's probably corrupted by some noise. It looks like as time goes on, the y function steadily increases, but it doesn't perfectly increase steadily. There's some noisy measurements there. And we'll return after the break to talk about how to choose that best straight line. And so I won't discuss regression in any more detail in this lecture. We'll defer that till after the break. But they both involve creating a function, namely the blue line, from the data of the red dots. So we're talking about functions. Let me just recap. Sarah presented a slide very similar to this last week, and all I've done is just change the notation ever so slightly. In maths, whether at high school or in your current maths courses, you've seen functions written in the following form, writing y equals f of t or f parentheses t. And the terminology is that we have a function, f, which takes what's called an argument and it returns a value. And so in this case, I like to think of t as time. So the function f, if it's given the value of time, will return a number, and that number is assigned to the variable y. And fortunately, but not coincidentally, the same terminology that's used in mathematics is actually used in the Python language as well. We talk about functions. We talk about functions taking arguments. In this case, just one argument, could be multiple, and returning a value. In fact, Sarah showed examples last week where a function can return multiple values. For today's lecture, functions take a single argument
and return a single value. So back up one slide, both interpolation and regression, but let's focus on interpolation, involves creating a function, a blue line, from red dots. So let's see how we go about doing that. So in the interpolation problem, I've said it in words, but now I'm going to get a little bit more precise about what I mean. Here's the interpolation problem. We're given data points, and I've written them here as a pair of numbers, a t value and the corresponding function value at that t. So at t naught, think of it as time t naught, the function y at t naught takes this value here that's indicated as the height on the vertical axis of this of the point corresponding to the time t0, and I've indicated that with the red dot. These are the red dots that I've presented in the earlier slides. So it's like we're given a function value at that point in time, and we're also given a function value at a second point in time. So the second point in time is t1. The function value at that time is y of t1. So we're just using the function terminology that we explained on slide 9 here. So we're given the two red dots, and we're also given this intermediate time t star, which falls somewhere in the range between t0 and t1. The interpolation problem is to calculate the value of the y function, an estimate of the y function, or the interpolated value at that time instant. So I've indicated that here as y hat of t star. T star is the time, the intermediate time at which we'd like to know the value of the function. And the hat is meant to indicate that at best we're going to be estimating the value of that function. We don't know what it is. We're only given the function values at the two red dots, corresponding to the two red dots. So the challenge is, the engineering problem is, to calculate the interpolated value of y star. And I've indicated that its actual value is the blue star here, meaning to convey there's some uncertainty about it, there's some mystery about it. We know the time at which it occurs, it's t star, that's the value that we're working with. We don't know what the value is, so it's got a question mark against it. And the interpolation problem is to, in general, is to come up with an estimate of the function value, not just at a particular t star, but at any t star that lies along this range. So we want a process that enables us to fill in or estimate the missing data at any point in time corresponding to these two red dots. Different ways of solving the problem, but the simplest way is what's called linear interpolation. It's called linear interpolation because we literally draw a straight line between those two red dots. And having drawn a straight line, indicated here in blue, having put a straight line between those two red dots, if we want to know the interpolated value or the estimated value at any time, intermediate time t star, we simply draw a dotted line up to see where the intermediate time t star intersects the straight line. And at that level, we draw a horizontal line across to the vertical axis, and that's our interpolated value. So linear interpolation, which is the form of interpolation that I showed several slides ago, where we had a line going up in sort of like it was heading up at different angles. Each of those angles was the slope of a line segment between two consecutive time steps. So linear interpolation in Python can be done in a number of ways. The way that I'm going to recommend, because I think it's the simplest and it's a very intuitive way of solving the problem, is going to use a function called interp1d. This is not LD, it's 1d. There are forms of interpolation that involve two-dimensional quantities, and I don't want to talk about those yet, but we will talk about them after the break. So interp1d, that comes from a library that we've not previously used. It comes from a library called SciPy. So SciPy is a scientific library. I think of it as like it coexists with NumPy. In fact, it uses some of the NumPy features, so it's sort of built upon NumPy. Inside the SciPy library is a module called Interpolate, which has got a whole collection of functions to do with interpolation. And so because we're using a function, interp1d, that comes from a library, SciPy, that we've not used before, it's important to do a pip install SciPy at the terminal window for the first time you use it. So you've done a pip install NumPy, you've done a pip install matplotlib, you'll need to do a pip install SciPy at the terminal also, just for the first time you use it, and thereafter it's in your virtual environment. Now, the beauty of using the interp1d function is that you can see the syntax of it in the grey box about midway through this screen. Interp1d, in its simplest form, takes two arguments. It takes an array t and it takes an array y. And so these are the arrays of time and the arrays of, I think of it as time. It's the horizontal axis and the vertical axis. So these two arrays allow us to access the red dots that we've been looking at in these curves. So we have a t array and a y array. And so in this case, we're going to actually do this live in a moment, we pass the arrays t and y to the function interp1d, and we get something back called f. And it's no accident that f is actually the function that we're interested in. So actually, interp1d does something really, really powerful, quite subtle, and super helpful for us. The call to interp1d actually returns a function. Now we've seen functions before which return values, numbers, ints, floats. And Sarah showed you last week how to write a function which returns an array from the function. Interp1d returns a function. So we call a function with a couple of arguments t and y, and we get a function back. And it turns out that that's really very convenient for using that function. So what I'm going to do now is I'm going to give you a live demo, and it's the function code is actually split across two lines, and so I'll step you through it live. It's in week 6 monlinear.py, and I'll just run that for you now. So this is the code's about 26 lines long, and so in the slides I've split it across two pages. So let me step through what the key elements are. We import NumPy as MP, we import matplotlib, .pyplot, so we've seen the first 2 lines before. Line 3, highlighted here in blue, is where we import the interp1d function. This is the function that's actually going to do the interpolation for us in Python. We import that from the scipy.interpolate module. And so you've got to do a pip install scipy before line 3 will work. Now, because I want to produce the same sequence of random numbers, I've just chosen a random number here, a random number seed. We saw the seeding of random number generators before. And I'm going to run, and you'll see now in lines 8, 9, 10, and 11, just going to fix a bug here. What we do is we set up our time base T. So let's, and then I'm going to skip over this line 10 for the moment. Going to skip over it for the moment. I'll come back to it and explain what that means. So we've got n, and n's the number of points. So if you remember the example I started the lecture with today, it had 11 data points. That n is the number of data points. And so line 9 sets up a time base, which has got 11 points spaced equally apart between 0 and 100. So 0, 10, 20, and so on up to 100. Then we generate a some random numbers. In fact, 11 of them. The third argument here is the number of them. Now, why do I generate that random that random noise? Because in lines 13 and 14, I specify the the coefficients of an equation which specifies a straight line. So the first part of line 15 is y equals m times t plus b. Now you might remember from school, you probably saw equations for lines that were y equals mx plus b. Here the t variable, think of it as time, is playing the role of x. And so I'm generating a data set here and adding some noise onto it. So what I'm going to do is I'm going to cut and paste those first 15 lines. I'm going to cut them and put them into the console, because I want to run it. I want to run it. I want to run the longer program in 2 chunks. So if I cut and paste the first 15 lines into the console, okay. So what you'll see on the right-hand side is I've got the various variables defined, but nothing's been displayed. So if I go down here in the code to the next, if I skip over the interpolation step for the moment and just take these 3 lines. So what I'm doing is let me pause. At the moment, I've created array T, and here you can see it's those 11 points specified between 0 and 100. And the y values corresponding to them are these values. I've generated them by creating a straight line, y equals m times t plus b, then adding on a bit of noise. So what you'll see if I plot now, if I plot ty, if I plot ty, no, I need to do it. I need to let me paste in this line here. Okay, so that plot function, the third line, the third argument R0 allows me to so I'm just gonna, it's just disappeared for me. So let me bring it back. Here we go. Let's try that again. Oh dear, one of those mornings. Here you go. So you can see I've plotted the 11 pairs of data points. So that's my data. So it's actually, it is actually, the reason why it looks like a straight line with some noise is because I generated it as a straight line with noise. So now, if I run all that code, and that was called week 6 nonlinear. It's reproduced the example that we saw earlier in the presentation. It effectively does 2 things. The first thing is to generate a random data set that's sort of it's a straight line with some noise. That corresponds to the red dots. That's the first thing the program does. The second thing it does is to take those arrays t and y and return a function f that does linear interpolation between the red dots. So if we now go back to the slides, I said the code was broken into two chunks. The first of which is what I ran for you in the console. I generate the data set. So at this point, we've got arrays t and y. And in the second half of the code, I do the interpolation. And so there's really, in slide 14 that you see in front of you here, there's only really two lines that are interesting or relevant to us here. The first one is line 2, where we pass in the arrays t and y, and we get a function f that's been returned to us. Line 8 looks pretty uncontroversial, but it's actually where all the action happens in this Python code. Because now, with our function f, we can interpolate between any of the red dots using this function f, and all we need to do is pass in either an individual time or an array of times at which we'd like to know what the function, the interpolated function value is. And so line 8 here, you'll see uses not the t-axis, but this time axis called t and u, which you can think of as a high resolution time array. And I defined that back in line 10 on this slide. It's the third argument here implies that between every two red dots, the t and u array has 100 time steps, 100 tiny little time steps. So you'll see that I can actually generate a plot, which is the interpolated values of the red dots by passing in the high-res time axis and the function value, the interpolated function value, here in line 2, at the high-res time, the time steps. So in fact, running that code from start to finish will produce the example that we saw back on page 6. Taking a data set and linearly interpolating between the points, having created the function f in line 2 here, we can then apply that to any time point we like. So let me show you how that works at the command line. The console. I'm gonna run all that code, cut and paste it into the console. Good. There we have it. And now what I can also do is say I've got a function f. It's got a I can actually apply that to any time I like. So I can apply it to time 0 and I get a value of 51.29. That's the first red dot. If I apply the function to time 10, I get the second red dot. Okay, so far so good. Sorry, let me put this into presentation mode so you can see the detail. Okay, so here I'll do that again. You can type, because we've actually got a function f now, which if we apply, we can apply time 0 to it, we get the first red dot. If we apply time 10 to it, we get the second red dot. Okay, doesn't look like very powerful so far, but what about this? What about if I choose a value midway between those, the time point midway between the first two red dots? I get a value that is on the line, the straight line between the first two red dots. What about if I choose time step 1, which is 10% of the way along the line between the first two red dots? I get a number back which represents that the linearly interpolated function. So that's really powerful, considering that once we'd set up the data set, this single line of code, a call to interp1d, returns this this function that we can then apply as we wish to any time we like. So we can choose a time midway between the second and third data points, and we get the value of the the point on the blue line connecting the second and third data point. So that's really powerful. Really very powerful indeed. And so that's linear interpolation. How to implement linear interpolation using the Interp1D function that comes from the SOAPI library. There's the code, and again I've popped that code into into the Discord channel this morning, and I'll post it on Blackboard at the conclusion of the lecture. So that's good. So the way I think of linear interpolation is it stitching together straight line segments. Now there's a mathematically precise way of saying that, but I hope you see what I mean by stitching together here is that we build up an overall function by gluing together consecutive or adjacent straight line segments that connect the red dots. So linear interpolation is the simplest form of interpolation, and it's done by stitching together straight line segments. Now that's good, but you can see that there's a problem with linear interpolation in that the slopes of the adjacent straight lines change very abruptly at the data points. So you can see that the gradients are constant, they change up, they change down, they always go flat sometimes, they go steep, but the point is that the gradient or the slope of the lines change at the red data points. And the reason for that is that with a straight line, you've got no other flexibility. If you want the line to pass through those data points, it's got to literally connect the two dots with a straight line. That's what linear interpolation is. There's no other flexibility to make the line smoother. Now it's possible to, instead of connecting the two dots with a straight line, it's possible to use a line that's a bit smoother, and the next obvious choice is a parabola. So you can imagine a parabola which is a quadratic polynomial. So instead of it being a straight line, it's either a convex, a curve up or a curve down polynomial, which has its endpoints at the red dots, but that's at least smoother between the transition between one parabola segment and the next. And so it's possible to stitch together quadratic polynomials so that it satisfies now two constraints. Adjacent parabolas should pass through the data points, the red dots, and they should also have slopes that match at the data points. So we avoid this very disjointed interpolation by using parabolas which smooth that transition. And while it's possible to do that with parabolas, it's very conventional to say, well, if we're going to use parabolas, let's use even smoother functions, cubic functions, which are degree 3 polynomials. So you get an even smoother fit to the data. So you have a data that fits, it goes through the data points, an interpolated function that goes through the data points, but it also has the slopes that match at the data points, and it puts some additional smoothness constraints on that make the overall stitching together very smooth indeed. Now, what I'm doing carefully here is I'm carefully sidestepping around some very interesting, but also slightly complicated mathematics. The mathematics of what are called cubic splines, which is what we're talking about here. The terminology changes to splines when we start stitching them together in this way. The mathematics gets a little bit trickier. It's normally about the level you would see in a second year engineering course. I mention that here simply to point out that there is some really interesting, and if you like that sort of stuff, challenging mathematics behind the scenes here. But it's a first year engineering course in using Python to solve problems. We're using the mathematical knowledge that's embedded in the Interp1D function to solve these problems without needing to be across the mathematics. So I'm very conscious that there is mathematics, but I'm also conscious that what I want this class to be able to do is apply the results in the first instance rather than worry about the mathematics of cubic splines. The cubic splines are really popular in a number of applications, including computer graphics, because what splines and interpolation in general allows you to do is to capture curves and in higher dimensions surfaces, and instead of having to specify the points on the surface at very high resolution, it's possible to store the surfaces as a collection of points, and then very quickly, when that surface needs to be rendered for a graphics application, to quickly calculate the spline and then plot only the values that are needed. So it's almost like a data compression algorithm where we replace a smooth curve with a smaller number of points that can then be interpolated if they wish. So splines are used everywhere. They're embedded in graphics programs and in graphics hardware. So what does it look like if you run a spline on the data set that we've been given? Here it is. I'll come back and look at the code in a sec. But with a cubic spline, we stitch together not straight line segments between the red dots, but cubic polynomials. So some of them look like they've got a curve. If you look carefully, some of them look like parabolas. Others of them have got a little bit of a kink in the middle. That's the characteristic of a cubic. It doesn't have just one turning point. It can have two. And so you'll see that this is the same data set. Let me go backwards and forwards between them. Here's linear interpolation, page 15. Same data set, page 18, with a cubic spline interpolated through it. So it's a much smoother interpolation. It doesn't explain the data. That's not its role. It basically just connects the dots in a smooth way. And the smoothness is important. Imagine if this was, imagine if we're talking about water level. Imagine if the vertical axis was a speed. Imagine it was the height of a rocket, for example, that was heading up away from the Earth's surface. You could argue whether the actual height was did the rocket actually move down before it moved back up? Probably not. But I would argue that a smooth interpolation is likely to capture the real behavior between the red dots better than this straight line interpolation. So cubic splines are wonderful, very powerful. The mathematics gets a bit complicated, but how about this? Let's look at the code for implementing the cubic spline in Python code. There is literally a one-line change between the linear interpolation that we saw in the earlier slide. It's one line out of that 25, 26 lines of code. The only line that changes is the one that's indicated here on line 2 of the code. So instead of calling the interp function ty, we add this third parameter, the text string cubic, and interp 1d does the magic for us. It also returns a function called here now f3 because it's a cubic polynomial. That's just my choice, but sort of makes sense. And then we can actually plot the interpolated value at those high-res time steps simply by applying the new function f3. So while the mathematics behind cubic splines gets a bit challenging, implementing a cubic spline in Python code is literally a one-line change from a linear interpolation, which is really very powerful. So now if I run the live demo of I'll do this for you live now. Week 6 Monday cubic. Here it is. The only line there are 2 lines that change. All this stuff at the top, generating the data set, exactly the same as it was before. Same random number seed, same algorithm. It's the same code. Line 18 here on the screen here, I've passed in this third parameter cubic. it returns a function f3, and then we apply f3 down in line 24. And that's the only change that's needed to get this to run in a cubic polynomial. So if we now run week 6 Monday cubic, same data set, and then we've got this lovely smooth interpolation that connects the dots. So really very powerful. Yeah, really powerful. And once we've gone through the setup, most of the code here, most of the code that you see is actually creating the data set. It's not actually doing the interpolation. The interpolation is done in one line. This code, which I'd encourage you to experiment with and reproduce the results and have a play with some of these numbers. The first 15 lines of the code's generating the data set. The interpolation itself is a single line. Wonderful. Cubic, we've done linear interpolation and cubic or cubic spline interpolation. Good. That's the first of the 3 things I want to cover with you today. The second of the 3 things is to discuss the assignment. I'll talk a little bit on the next page about what the assignment's about, but I want to give you a clear sense at the moment of how you go about the assignment, because it's an assessment item, the likes of which we haven't seen in this first 5 weeks of the course. So I want to tell you about how you go about solving it, how you go about submitting your answer, how it's assessed. So it's released today, and if it's not on Blackboard, it will be shortly. It'll be in the, and I'll make an announcement about where to find it, but it's released today. You now have 3 weeks to complete the assignment number 1. And then when you're ready to submit assignment 1, what you do is upload a Python file to Blackboard. And then everyone's got the same submission date for the Python file. It's uploaded to Blackboard no later than 9 AM, Monday, the 19th of April. So we've just ticked past 9 o'clock here. It's almost 10. So you've got almost 3 weeks till Monday, the 19th of April. It's the first Monday after the semester break. And so everyone has the same deadline for submitting their Python code. The way that it's assessed is that in the face-to-face computer lab after the recess, and I'll talk about online students and students that are unable to attend their face-to-face computer lab, we'll do that down the track. But for the overwhelming majority of you, in week 7, which is the first week after the recess, your project is assessed by you sitting down one-on-one with a demonstrator and demonstrating the code that you uploaded to Python earlier in the week. So that's a very fair method of assessment, because everyone gets the same submission deadline. And then on the day of your lab, whether it's Monday, Tuesday, Wednesday, Thursday, Friday, you download the code from Blackboard and you run it for the demonstrator, brief demonstration, and the demonstrator will mark it according to a grade sheet, a rubric. We haven't yet released that rubric, but that'll happen in the coming days. Certainly you could comfortably get started on the assignment without knowing what the rubric is. One aspect of the project that is, I would say, is unlike the assessed lab that we did back in week 4, and indeed the quiz later this week, one aspect of the project that is unlike those assessment items is that we're explicitly calling out some content of the assignment that's advanced. So if you want to attempt the assignment and do a basic job and get a middling sort of mark, that's your choice. There's also going to be some more advanced questions built into the assignment towards the end of the assignment question sheet that allow you to extend that material and spend more time on it, higher level of achievement, demonstrate your knowledge at a deeper level, and put yourself in line for a higher course grade. The details of that, again, will be embedded in the rubric that we release in the coming days. But just putting that out there now, if you are aiming for a high mark in this assignment, then you're going to have to work for it. That'll mean using the knowledge that we've presented in lectures, but to do it in a more advanced way. You'll have seen already in some of the lab sheets that some of the questions are harder than others. That's deliberate. Not all engineering problems come at the same level of complexity, and not all students spend the same amount of time on the course, to be blunt, and that's okay. But I want to give the opportunity to students who do want to spend more time on the assignment to have that opportunity to test their knowledge, to extend their knowledge, to demonstrate their knowledge at a higher level, and that'll be apparent in some of the questions in the assignment. It's not all hard. In fact, the assignment sheet you'll see is actually very step by step. It leads you through the initial steps, how to get the data set, how to process it. But towards the end of the assignment, there's some extension questions which they're not quite open-ended, but they give a lot of opportunity for students who want to put more time into the course to demonstrate their knowledge at a higher level. Oh, and the assignment does count for 20% of the course grade. That's substantial, and so you can anticipate putting a bit of time into this assignment. It's 1/5 of your overall course grade is on this assignment. So the topic of the assignment is analysing GPS data, positioning data, map data, and so that's an application that's applicable to all forms of engineering, whether you're an electrical engineer, a aerospace systems engineer, a mechatronics engineer, or any other types of engineering that students we've got in the course. That data is equally applicable to you. So in a little bit more detail, it's GPS data collected during a mountain bike ride, and I have my teaching colleague Brenton to thank for collecting that data live on a mountain bike ride that he did recently. And what Brenton has done is prepare the track log from his GPS tracker. It's presented in a CSV file, and we saw a couple of weeks ago how to read CSV files, where the data in each column represents a different physical quantity. In this case, there are time steps, latitude, longitude, and elevation, how high above sea level Brenton was on his mountain bike ride, recorded at 1 second time intervals. And the essence of the project is to ask you to analyze that GPS data, much like a fitness tracker. There's some issues with the data. Some of the data is missing, so you get an opportunity to use interpolation should you wish. The GPS signal was lost. You'll be able to perform some calculations with the data in order to give the sort of information that you might expect out of a fitness tracker. So we're really excited about this assignment. It's real live data, and you'll get an opportunity to plot that data, and in the more advanced aspects of it, to overlay that data onto a map. So it's really quite exciting, very accessible. It's real data. Brenton collected it himself on a mountain bike ride, and so it's real data, and associated with that comes issues like missing data, for example, where the interpolation's needed to fill in the gaps. So we've therefore made a decision that for the computer labs that run this week, both the face-to-face and the Zoom labs, there's no week 6 lab sheet. That's deliberate. The assignment 1 question sheet is effectively your lab sheet for this week. We want you to get started on the assignment in place of the lab sheet. And so a highly recommended goal for you for this week is to finish the week with a clear idea of what assignment 1's asking. Certainly don't expect you to complete assignment 1 this week. You've got 3 weeks from here. But it's important on these bigger projects to get started early. You don't have to make, you don't have to, as I say, you don't have to do it this week. But my strongest possible recommendation to you is this week, that if you get to the end of the week, your goal should be to have accessed that file. It's available. It'll be available, if not already, on Blackboard. I'll send out announcements where you can find it all, but it'll be on Blackboard. Your goal for the week should be to have downloaded that file, imported it into Python using the pandas library, examined that the arrays, which are the time steps, the latitude, the longitude, and the elevation. Is the data there? Does it look right? And then plot it. That's your goal for the week. Now, you might make greater progress, and you are stepped through that process in Lab Sheet. So it's not like we just throw it to you and say, go for it. You are stepped through the individual steps. Your goal for the week, my advice to you, is to get as far as you can down the track with the assignment, because you've got the computer labs to do it. It's a great opportunity to put your hand up to the demonstrator and say, I don't understand this. How do I get this data? It's not displaying for me. How do I import it? Where do I put the CSV file? If you can do that this week, you're off to a flying start, because you can't analyze data until you've got it in your programming environment. So that's my strong recommendation to you this week. And the lab sheet has got lots of detail and steps you through the process, and we'll be monitoring Discord for any bug tweaks that need to be ironed out in the question sheet. 3 weeks today, it's due. You're assessed in week 7. Final topic for this morning's lecture. I said this morning's lecture is going to be a bit shorter. That's deliberate. Don't want to overload you with technical content in a week when you've got a midterm quiz. So the midterm quiz, it's scheduled for this Thursday, the 1st of April, 4 till 5 p.m. I'll say more about the timing in a moment. It is during the scheduled lecture time, and the midterm quiz will run in place of Thursday's lecture. So there's no Zoom or YouTube live stream on Thursday at 4 o'clock. Normally, we'd be saying we'll catch up next on Thursday at 4 o'clock. That is not happening this week. The quiz is done entirely on Blackboard. No Zoom, no YouTube live stream, no lecture this Thursday. Midterm quiz happens instead of Thursday's lecture. So what happens is, on Thursday at a bit after 4, the quiz magically appears on a timer at 5 minutes past the hour, and it'll disappear again at 50 minutes later. So you've got 50 minutes to complete the quiz. Now, we've written in a way that if you are across the material, 50 minutes is more than the time you'll need. It's an open book quiz. What that means is you've got same deal as the assessed lab. You've got access to all your code that you've written through the semester, your solutions, to the lab sheets, all the lectures, all the recorded lectures, the lecture notes. You've got access to it all. Keeping in mind that in 50 minutes, you don't want to be starting from scratch with getting your head around that content, because you've only got 50 minutes, but it's all available to you. The things that are not available to you are Discord and other online platforms where you say, for example, can someone help me with the answer to this question? That's not on, that's plagiarism, that's collusion, and we'll be on the lookout for that, just to be completely transparent with you. And that's the way the quiz will run. So don't expect Zoom or YouTube. The quiz will appear on Blackboard at 5 minutes past the hour on 4 on Thursday, and it'll disappear at 50 minutes later. I'm aware of a number of students who have unavoidable commitments on Thursday, and we're working to set up a backup time. I'll say a couple of words about that. I'm caught in a difficult position. The university policy on what the university calls usual employment is very clear. Employment doesn't count for adverse circumstances for assessment items. University is very clear on that. It puts me in a difficult position because I know that part-time employment is not easily shifted, and I know it's not easily foregone. My expectation is that the overwhelming majority of students will be completing the quiz on at 4 o'clock on Thursday rather. There'll be a backup, not a supplementary, but a special sitting time for a small number of students that that have contacted either me or the other members of the teaching team. I'll be clear about what those hours will be later, but you can fully anticipate an evening quiz for those students. It won't be at a pleasant time, but the more pleasant we make it, the more likelihood of we'll have someone saying, yeah, well, my part-time job was at 4, but it's also at 6. So we're going to be pushing it back into the evening. And I want to be clear that my expectation is the overwhelming majority of you complete the quiz at the scheduled lecture time. That was the time that was in the course outline that was released 6 weeks ago. And that's the time that my expectation is that you'll complete it. For the relatively small number of you that can't make it at that time, and I've been in contact with some of you already, we're working to have a later sitting time for that. The constraint, of course, is that Friday, the day after, is a public holiday. So it's not possible for us to shift it back and have that quiz run on the Friday. Okay. So what does the quiz look like? I'm going to be really upfront with you about how the quiz is going to look. And we've actually put a practice quiz on Blackboard this morning for you to get an idea of what the form of the quiz will take. So I'm being really, really clear and transparent with the whole class right now about what form the quiz will take. The quiz is going to ask you to write some Python code. And what that's going to involve is loading a CSV file, one of these comma-separated variable files. We've seen those a couple of weeks now, and they were included in a couple of the consecutive lab sheets, the computer lab sheets. So we are going to, in Blackboard, give you a CSV file. In fact, it's going to be one file that's distributed to the whole class. We're then going to ask you to perform some calculations on a specified column of that CSV file. So we are going to ask you to do some array processing. We've looked at them. If you look back at the last couple of weeks since we've introduced arrays, we've computed functions with arrays. We've done some looking at different. Sarah had some examples last week where she did some. She stepped you through processing of looking for particular values in arrays, or computing quantities that needed some or all of the values in those arrays. And the reason that we give you access to one big CSV file is that every student in the class is going to be assigned a unique column in the file. That means that the answers that you submit will be dependent on you as an individual, rather than every student getting the same data to work with. And so once your program's complete, you're asked to do two things. One is that you enter the results of your program into Blackboard, and I'll show you what that looks like in a minute. The second thing is that you're asked to upload your Python code into Blackboard. And so, unlike the assessed lab, you'll be doing a Blackboard quiz on Thursday. You'll press submit, and then we'll mark the mid-semester quiz will be marked offline. It won't be marked on the spot. So when you press submit, you'll get an indication that your submission was received correctly by Blackboard. Thank you very much. But you won't get your mark on the spot. We'll be marking those submissions. So there's a practice quiz on Blackboard now, and I encourage you to go there as soon as your calendar will permit. We've set it up to be, it's a sample. There's a CSV file there you can work with, you can download. You can put in the place that it needs to be so your Python code can find it. Keep in mind that the CSV file that we've got on Blackboard in the practice quiz is not the one that we're going to distribute to the class on Thursday, but the process is the same. And you can practice that practice quiz now on Blackboard as many times as you like. It's not assessed. We don't look at what you submit. You can have a go at it. You can understand the process. To be well prepared for Thursday's quiz, you've done that practice quiz a few times and you know the process. Here's how I take a CSV file. Here's how I read it. Here's how I read a particular column. I can do some processing on that array, and I know how to upload the results into Blackboard. So let me show you what it looks like inside Blackboard. Here's Blackboard. Now keep in mind that my Blackboard looks a little bit different to yours because I've got the ability to edit as a course coordinator. But if you go to the assessment tab, let me see if I can just increase the zoom on this a bit. That might help a little bit. On the left is an assessment tab. And right at the top here is an example quiz. So this is going to look like, it's not the real thing, but it's going to look like the quiz that you see on Thursday. So you click on that link. It says there, you may attempt the quiz as many times as you like. Marks won't be recorded. So you click on the example quiz and it says some instructions, blah, 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 blah. It's give you some experience, marks not recorded for the practice quiz. You press continue, and what you see is 2 questions. Question 1 asks you to download the CSV, and here's the link to the CSV file as part of question 1. This is just a test. You then run some code and you type your answer in, you run your code and you go, my answer is 123. Great. And then you cut and paste you've written your code in PyCharm, and let's just type in some code from today's lecture. I'm gonna copy it and I'm gonna paste it into the window, and it gives me 2 options, either remove or keep formatting. It doesn't matter which one you choose. You can choose either. It doesn't matter. I'll show you what they both look like. Let me see if I remove formatting. There's my Python code in the question 2 box. Save and submit. It says OK, and then you can press OK again, and you'll see there's my selected answer, and here's my code. Safely cut and paste into Blackboard. I'm done. So there you go. Example quiz. Let me do it again. Begin. This time, there's the CSV file that I need to download, write my code. I've got 50 minutes to write it. This time my answer is 456. I'm now going to paste in the code, and suppose I keep the formatting this time. It doesn't matter whichever option you choose. If I keep the formatting, it's got the dark font and the colors. Save and submit. OK again, and then get the indication. There's my number that I entered, 456, and here's the Python code safely cut and paste into Blackboard, and that enables us offline to go back into your submitted answer and behind the scenes, copy that code into a Python console and check that your code generates the answer that was here in question 1. So that is the way that the midterm quiz is going to operate. Now, there's a number of little details that we'll talk about that are probably best done by announcements on Blackboard, class emails, and also some follow-up on Discord. Now's not the time to dig into all those details because I know there will be there'll be some questions associated with what if this, or what happens if I forget to do that, or can I do this? We'll do that offline. I just wanted to give you the overall sense of what the quiz process will look like. And so we'll have a timer set up so that the real quiz will be set to appear at, as I say, 5 minutes past the hour on Thursday, and it'll disappear 5 minutes before the hour. So you get the full 50 minutes, and it will take this form. Now you'll see there's things I've deliberately not been transparent with you about today. I've not given you the actual CSV file. I've given you a CSV file in Blackboard. There'll be a different one there on Thursday. I've not said what these sum calculations are. You can probably have a guess, but I'm not going to tell you those sum calculations in advance. But I can say that if you're across the material that we're presented in lectures in weeks 1 to 4, you'll have no problems guessing and answering those questions. And I'm not saying how we're going to go about assigning each individual student a unique column in that spreadsheet. Again, you might want to guess. Your guess might be right or it might be wrong. It actually doesn't matter whether your guess is right or wrong. I'm telling you now, you're going to get a CSV file. You'll be given enough information in the question to be able to identify for you as an individual which column is yours. You write your Python code. You then enter the results into the first text box. Might be more than one text box, might be 2 or 3. And then you upload your code. So that behind the scenes, after the submissions are all in, we can then grade the results. Do the results match what we anticipated? Are they correct? Do they match these sum calculations? Do the answers that you entered into Blackboard, do they match the calculations that we asked you to perform? And if need to, we can actually run your Python code because you've uploaded it into Blackboard. So, end of today's lecture. Super quick summary. We looked at interpolation with the straight line interpolation and cubic spline. Cubic spline is a lot smoother, but it's actually no more difficult in Python than linear interpolation. And I can anticipate at least some of you will be using interpolation, be it linear or cubic spline, in the assignment. So that's why I wanted to give it to you today. Present that content for you today. Assignment 1, we release it today. Its submission's due in Blackboard 3 weeks out. The midterm quiz, which I suspect will be the focus of many of your minds this week, and rightly so, counts for 15% of your overall course grade. Done on Blackboard. Some of you will do a later sit, but the overwhelming majority of you will be at 4 o'clock this Thursday in the scheduled lecture time. And I encourage you in the strongest possible terms to have a go at the practice quiz, do it multiple times, get some practice to know what it feels like to submit your answers in the checkbox, in the answer box, to submit the cut and paste your code into Blackboard, because that's what you'll be asked to do on Thursday. Thanks so much for your attention. It's a big day in terms of setting you up for some assessment items that cover a good chunk of the overall course grade. And I'll be in touch on Discord, and I won't see the rest of you. See you on Thursday, but we'll be online on Thursday monitoring the progress of the midterm quiz. Until then, I say good luck and have a good week, and good luck in preparing for the midterm quiz. Bye for now.